All right. So let's see. Last time we discussed the ordinary point. I mean, yeah. So there were. Let's see. Let me write down the differential equation. d2 u by dz2 plus p. So that's the differential equation. And p, we said, so the first point we discussed was the two solutions to the fundamental solutions, independent solutions, around ordinary points. This we did that first. Ordinary points are the points where P and Q are both analytic around that point. So here P and Q are analytic. I mean, this was just a definition of the ordinary points. And then in then we started discussing the regular singular points. So when P, so around regular singular point, which means P has at most first order pole, has at most first order pole, and Q has at most second order pole. There we started discussing, and I think we arrived at the indicial equations, right? So two things. So what this means is that P, so therefore I can write P is equal to A naught over Z minus Z naught plus A1 plus A2 Z minus Z naught, etc. Because of the first order pole, so we have, this is just a definition of these constants. I mean, I just defined them as A0, A1, A2. Let me just write it down. I think that was crucial. So first of all, we defined A, which is equal to Z minus Z naught times P. Since P has at most first order pole, A is analytic, and therefore it will have a Taylor expansion, right? And in fact, we defined this as A and Z minus Z naught to the n, 0 to infinity. And similarly, B, we define it as Z minus Z naught square, Q. Once again, Q is at most second order pole, so this is analytic, right? And this we expanded as B and Z minus Z0 to the n. Yeah. So this was the thing. So let me erase this. Yeah, this is already defined there. And then when we, so what we did was we looked for a solution of the form U, a power series solution. There is some starting power R, and then we have an expansion, and I think we were calling it a Cn, Z minus Z0 to the n. So we are looking for a solution for the U near Z equal to Z0 of this form. And then we found that this R was not arbitrary. R had to satisfy indicial equation, which was a quadratic equation. So it had two possible solutions. So maybe I should just write down what those equations were, not to repeat. I think we did that in detail, right? So I will not spend time on repeating it. So I will just write down the equation. So by plugging it in here, using the P and Q from these expressions, we find that the main equations were, this main equation was, yeah, so n plus r times n plus r minus 1 Cn plus plus n plus r A0 plus B0. This whole thing multiplying Cn was plus sum n equal to 0 to n minus 1 m plus r A n minus m plus b n minus m times Cm equal to 0. right? This was the where it is understood that, I mean, this term exists only for n greater than or equal to 1. Because, I mean, if n equal to 0, this doesn't make sense, the sum from 0 to -1. So this exists only for n greater than or equal to 1. The second term only exists for that. I mean, that this is just obtained by plugging in. It's just a mechanical, I mean, just putting the terms together, and, you know, it's nothing. So this is just equating the, I mean, you just plug in everything here, and you see you're just equating for a given power of z minus z0, you're just equating the coefficients from each side, each of these terms, and you get that equation. Okay, so in particular, if I look at n equal to 0 term, see, there is no, this is absent because this sum is not there. So for n equal to 0, you have only the first term, and that tells me that r times r minus 1 plus r a0 plus b0 times c0 is 0, but c0 by assumption is not 0, because that was the, I mean, this r was by definition the leading term for the u, but then I mean, then one is assuming that c0 is not 0. If c0 was 0, then it would have been the next power, right? R plus 1, because if, suppose c1 was the first term which was not 0, then it would be r plus 1 power. In that case, I would call that r plus 1 as the r, I mean, the leading term, right? So therefore, c0 I always, by assumption, by the statement that this is the leading behavior, I am already saying that c0 is not 0. Okay, c0 is not 0. So that means that r must satisfy this quadratic equation. I mean, this bracket must be 0, right? And there are two solutions, and you can see that, well, just rewriting this, you get here r square minus 1 minus a0 r plus b0. That's equal to 0. This is a quadratic equation. It will have two solutions in general, two complex solutions, r1 and r2, which will satisfy, of course, r1 plus r2 is equal to 1 minus a0, and r1 r2 equal to b0. That's the two roots. Okay. Now, okay, we just gave again a name. I mean, of these two roots, I will call one of them as r1, other as r2. Which one? I will. So if I look at the real part of this equation, so the real part of this equation is real r1 plus real r2 equal to 1 minus real part of a0, right? So I will call I will put the label 1 to that root whose real part is the larger one, the bigger one, bigger or equal to. I mean, if the two roots could have the same real part, in that case it's arbitrary. You can just call any one of them as r1. But in general, they will not be equal. The two real parts will not be in general equal. So whichever is the larger one, I call that as r1. That's just a convention. We have chosen a convention to define like this. Now, so real r1. So the point is the real part of r1 is greater than or equal to real part of r2. So this is my convention. This, of course, means that implies that real part of r1 is greater than or equal to 1 minus real part of a0 divided by 2, right? Because I have a sum of these two terms equal to that, but I'm saying that this part is greater than or equal to that, right? So therefore, this must be greater than or equal to half of that, right? That's I mean, I will just need, it's not important right now, but I will need it. I mean, I will use it to prove the convergence, fine, because we need to prove the convergence, right? By the way, I mean, I must caution you that, I mean, when we wrote this series and we plugged it in here, we actually commuted the differentiation with the sum. We did the differentiation of individual terms. That is, I have not justified yet. I mean, that will be valid only if the series was uniformly convergent. What we will show is that we'll assume that at the moment we assume that the CNs are such that the series is uniformly convergent, so that I can commute. And later on, we'll prove that in fact the CNs that we get from these equations, right, they are such that the series is uniformly convergent. So it will be justified later, this operation of commuting the two things. Okay, so now the point is that you see, for this if I choose, so R has to be either R1 or R2. Otherwise, already my first equation becomes inconsistent, right? Now, if I choose R equal to R1, then you see these equations can be used to determine all the Cn's in terms of C0, right? Okay. I mean, when can there be a problem? So what is this equation? This equation tells me that if I know all the Cm's up to n minus 1, right, then this equation allows me to determine Cn, right? So this way you recursively determine all the higher coefficients. But the only problem could be that maybe for some value of n, this may be 0. If it becomes 0, you cannot determine Cn from that equation, right? But the point is that if I had chosen R1, I mean, so look at this part. This is the same as that, except this R has been replaced by n plus R, right? So think of this equation. This equation, maybe I shouldn't, this quadratic equation is simply x squared minus 1 minus a0 x plus b0, right? I consider this is my quadratic equation. And R1 and R2 are the only two solutions of this equation, right? Now this equation is the same as that, except x has been replaced by n plus r, right? So for this to be 0, n plus r must be again equal to either R1 or R2, because those are only two roots. But if I had chosen R1 for R, then the real part of n plus R1 is of course going to be greater than real part of R1, right? So it can never be equal to R1. I mean, this cannot be equal to R1, right, because n is positive, and also it cannot be equal to R2, because real part of R1 is greater than or equal to real part of R2. So it can never be equal to R2 or R1. So there will be for no value of n, this will be 0, okay, and therefore I can determine Cn for all n. We can determine. Okay. So is that argument clear? I mean, so let's see. So we are asking the question: is it possible that there is some value of n for which this is 0? Okay. Well, if that is the case, then n plus r must be a root of this equation, because this is the same as, you see, this is the same as r replaced by n plus r, right? So we are saying that n plus r must be a root of this equation, but there are only two roots, r1 or r2, right? So this must be either r1 or r2. It cannot be equal to r1 if I have chosen r equal to r1. You see, I'm saying that I have chosen here r equal to r1. Okay. Then this is n plus r1. So since for n positive, that is the case we are looking at, because we want to determine all this Cn for n positive in terms of lower ones, right? So for n positive, n plus r1 is obviously not going to be equal to r1, right? And it's also not going to be equal to r2 because of this condition, right? Because real part of n plus r1 is of course even greater than real part of r1, but this is greater than real part of or equal to real part of r2. So this can neither be equal to r1 nor r2. So this cannot be 0, right? This is the logic. And therefore I can determine all the Cn's. Okay. So the solution is unique, right? Because I'm determining all the Cn's in terms of C0. Why in terms of C0? Let's say take n equal to 1. So that tells me that C1 I can determine in terms of C0. Then I go and put n equal to 2. Then C2 can be determined in terms of C0 and C1. I mean, this m goes from 0 to n minus 1. C0 and C1, but C1 I have already determined in terms of C0 from the previous equation. So therefore I see that C2 is given in terms of something times C0, right? And so on. You can keep recursively obtaining all the Cn's in terms of just one constant C0, right? So the solution is uniquely determined up to a constant C0, but that's not, I mean, it's a linear equation. So given a solution, you can always multiply by a constant. So this gives you a unique, one solution. Provided, of course, we have to show that the Cn's that you determine from these equations are such that this series is uniformly convergent. Right? This is the only thing which we need to show. So that is okay, one solution. Now what happens? I mean, here after all there are two possibilities. I could have chosen r equal to r2, right? But if I choose r equal to r2, so let me see. So for r equal to r1, this coefficient of Cn, I mean in that equation, is never 0, and therefore this implies Cn can be determined. Right? However, when you choose r equal to r2, now it's no longer true, because now you see here you have n plus r2. Right? Now, for this to vanish, this must be a root of this equation, which means either r1 or r2. It cannot be r2 because n is positive, right? But it can be r1 because a real part of r1 is greater than or equal to real part of r2, right? So it could happen that n plus r2 is equal to r1 for some n, right? In that case, I cannot, this vanishes and I will not be able to determine Cn, right? But when can that happen? That can happen only if r1, difference between r1 and r2 is an integer, right? So yeah, so so that will happen only if r1 minus r2 is an integer, right? Otherwise, there is no problem. If r1 minus r2 was not an integer, right, then this will again never vanish, and then you can determine all the Cn's, right? So the only subtle point is when the difference between the two roots is an integer. Then this method doesn't work for the second solution. For the first solution, it still works, but second solution will not work. And then we'll use the approach that we, what was it called, the variation of parameter method, some method like that, right, using the Wronskian. So we will use that to construct the second solution in that case.
So why we use, I mean, usually we expand using processes like integers. Why not we use like rational numbers?
Rational numbers. No, this R is any number. I mean, may or may be rational. N equal to 0 to infinity. So what we are saying is that, so we want to write whatever, I mean, so okay, when P and Q are not analytic, which is the case we are studying in basically here, in that case you don't expect U to be analytic, right? You expect U to have some singular behavior. But what I'm doing is I'm taking this, I'm including all the singularity here, and then what multiplies is this is an analytic function. So I'm assuming that there is a form like this. Okay, of course, this is an assumption that this is what is called ansatz. I'm making an ansatz for this U, plugging it in, and finding that ansatz works, at least for r equal to r1. For r equal to r2, it will not, when the difference between r1 and r2 is an integer, this will not work, and we'll see that this ansatz is not good enough. For the second solution, this is not good enough. It will be, yeah. Yeah.
But if, I mean, can we do like if we include by half or something?
No. I mean, so, well, I mean, okay. Of course, suppose for example, r2 was equal to r1 minus half, just as an example. In this case, the r2 will also give you another solution, right?
Yeah.
Because its difference is not integer. So now you have two solutions. One, u1, which starts with the z minus z0 to the power of r1 times the series solution. I mean, this is a sum of the series solution with integer power difference.
Yeah.
And another solution, u2, which starts with z minus z0 to the power of r2, which is r1 minus half. Okay, times again. Of course, if you take the sum, any arbitrary combination of them, then that will have no definite, I mean, it will have both integer and half integer expansions, right? So this is an ansatz, I'm assuming. I'm saying that this is an ansatz, but that makes sense, you see. I mean, it's okay to look at such an ansatz. Why? Because, I mean, this, if you plug this in the differential equation, I mean, suppose you had also put here Cn plus another one, let's say Cn plus half or something like that, times z minus z0 to the n plus half, suppose you had put it. Then when you plug it in this differential equation, you will find relation between Cn and Ca. I mean, you will find relations between only the integer Cn's separately and half integer Cn separately, correct? So it's like doing two independent solutions, you're adding them together. And why is that so? The reason is when you plug it in here, these derivatives are going to only shift these powers by integer unit, right? And the P and Q, we have assumed the P and Q are only meromorphic. If P and Q had branch cuts, if P and Q themselves had multi-valued character, they were multi-valued around some point, in that case these answers will simply not work, right? But because it's meromorphic, when you make a Laurent expansion for P and Q, they're again in integer powers. That's the reason why this works. Okay. Fine. So let's. So maybe I should first discuss the convergence problem here for the C1, for the U1. I mean the R equal to R1 solution, and then for the U2. I mean this I will call U1, the one which corresponds to R equal to R1, and U2 is the one which corresponds to R equal to R2. Yeah? And U2, as I said, we'll determine by using the Wronskian method. We won't use this method. So first, since this is in the blackboard, let us try to get an estimate for, I mean, to show that this series is convergent. Okay. So here is the series. Okay. So we want to, of course, make an estimate for this Cn. So for this, I need to make an estimates for these guys, a n minus 1, b n minus 1, all these things, right? Where a's are a and b are defined like that. Okay. So remember, these are, of course, after all, these are the Taylor expansion. These coefficients are Taylor expansion coefficients for analytic functions a and b, right? So in fact, last time I wrote down an integral representation. I mean, we know how to compute the Taylor coefficient, right? So Taylor coefficient was, so a n is integral, say 1 over 2 pi I, some close contour around z naught of a over z minus z naught to the n plus 1 dz. Yeah, and this gamma is a circle. I will choose it to be a circle centered around z naught. So gamma is a circle of radius r centered around z naught, centered at z naught. Okay, and it's exactly the same expression for Bn with just A replaced by B. Okay, so now we can get an estimate absolute value of a n. Well, since capital A and capital B are analytic functions in this region, circle is inside that region where I'm choosing the circle gamma inside the region where capital A and capital B are analytic. This is of course possible. I can always find it because by assumption this z naught is an isolated singular point. So there will be some neighborhood in which there will be no other point where the P and Q have a singularity, right? So you can always find such a circle, and then so we get an estimate. So let's say, for example, a n. So since A and B are analytic, in the region where gamma is, they're obviously bounded, right? In that region, on the circle, it's bounded. So let's suppose lambda 1 is the max of A, and lambda 2 is the max of B on the circle on gamma. Okay. Correct. Is there factorial? No, there's no factorial. No. Yeah. That yeah. Okay. So therefore, absolute value of a n will be, okay, there's a 1 over 2 pi, and on the circle I can always write z minus z0 equal to r times e to the I theta, where r is the radius. So on the circle z minus z0 is capital R times e to the I theta, and we have to integrate between theta between 0 to 2 pi, right? on the circle. So let's see how many r's are there. There is r to the n plus 1 from here, but from the change in the measure you get a r. So you get here r to the 1 over r to the n, right? So there's a 1 over r to the n. Max of A is say lambda 1. So this is less than or equal to, and less than or equal to lambda 1 times the integral of theta, which is 2 pi. So 2 pi cancels. That's the estimate. So this is a bound, upper bound for an, and similarly for bn, the upper bound is absolute value of the bn, upper bound is lambda 2 over r to the n. That's the first thing. Okay. So now let's see. We want. Can I erase this? So let's see. I mean, let's call this this is something, right? It depends on n. Actually, okay. So Cn from this equation is minus. Take all of this on the other side. Say m plus r, a n minus m plus bn minus m, Cm divided by this quantity. This sum is going from m equal to 0 to n minus 1. So this is the Cn, right? So if I want to get an upper bound for Cn, I should have upper bound maximum. I mean, I should look at the upper bound for the numerator and the lower bound for the denominator, right? I mean, the lower the denominator is, the total thing is higher, right? So in order to compute the upper bound of something, you look at the upper bound of the numerator and at the same time the lower bound for denominator. So remember here I have chosen R1, right? Everything is R1. So really I should put here R1. Well, if you open this up, the denominator, let's see, maybe I should now, I can erase this part. Let me just write down this estimate here. An is less than or equal to lambda 1 over r to the n and bn. Where lambda 1 and lambda 2 are max of A and B. Maybe I can just write max of A. And the circle. Okay. So the lower bound for this, let's simplify this. This expression is same as you have n square plus a linear term in n is n times 2r1 minus 1 coming from here. I mean r1 plus r1 minus 1, and then from here is plus r1 a0 plus r1 sorry, plus a0 is correct, and the last, that n independent term vanishes, of course, because that was the R1 was satisfying the quadratic equation, right? So that's what it is. The denominator is this. But remember, 2R1. Remember that equation, that R1. I mean, this expression is less than. If I take the absolute value of that, right? Absolute value of this is going to be greater than or equal to n square, right? Why? Because we already had this relation, real part of R1 is greater than or equal to half of 1 minus A0, real part of 1 minus A0, right? So if you look at just the real part of it, I mean, this is the absolute value. So there will be real part plus the imaginary part square. So the real part, n is of course real. So you have n square plus n times the real part of 2r1 minus 1 plus a0 whole square plus n square times the imaginary part of 2r1 minus 1 plus a0 square, right? Square root of this whole thing. That's absolute value, right? The real part of this square plus the imaginary part of this square and the square root. That's what it is. Now, this guy is already, this guy is positive from this equation, you see? I mean, multiply by 2 and take it on the other side. So this says is positive, right? So this is n square plus n times something positive whole square plus n square times again something positive square, right? So this is this part is already greater than n to the 4, right? Is that correct? Did I make a mistake? Just 1 second. Yeah. Yes, this is correct, right? I think, yeah, this is sign is correct. So this is positive. Okay, I bring it to the other side. So this is greater than or equal to 0. That's what that equation says. So this quantity is positive. So it's n square plus something positive n whole square, right? N is of course positive. So this says that this is greater than or equal to, so this is, the first term is greater than or equal to n to the 4, right? When you add this again to n square plus all that, this is again positive. So once again, this entire thing inside the square root is greater than or equal to n to the 4 inside the square root. So the square root is greater than or equal to n square. So that's the way you prove that is greater than or equal to n square. So that is the lower bound for the denominator. It has to be at least greater than or equal to n square. Actually, I'm being very, what do you call, liberal with my estimate. In fact, it's much, much bigger than that. But okay, it's enough for us. Now, the numerator, we use this condition here. I mean, so let's say that take the numerator. So it's you have m plus r1. So the numerator is m plus r1 modulus, okay, which is the same as m plus modulus r1 times modulus of a n minus 1 m. I'm just looking at this particular coefficient. Okay, then it will multiply modulus of cm, right? Plus modulus of bn minus m. This whole thing is going to multiply modulus of cm, right? So the idea is if I take the modulus of that, that's going to be less than or equal to, well, that's going to be equal to the modulus of this whole thing. But the modulus of this whole thing, modulus of the sum is less than or equal to sum of the modulus. No? So you'll get so there will be a term like this. I mean, this will be summation over m. But now I use this estimates there, this upper bounds for a. So you find that this is less than or equal to m plus r1 modulus to the times the max a, which max a. Okay, let me keep it sort of introducing too many symbols. R to the n minus m, right? Plus max b over r to the n minus m. This whole thing multiplying cm, right? That is the individual term, but now I have to sum this up from m equal to 0 to n minus 1. So that's the kind of equation we have. So let's see the structure of this. So let's see what are we saying here. So for example, C1. So what we are saying, so n equal to 1. So C1 is less than or equal to modulus of C1. So n equal to 1, there's only one term, m equal to 0 term. Okay. So that gives you, maybe I should write down something. So let me take out, okay, first let me write down this whole thing. Cn modulus is less than or equal to what we are saying. Denominator we already proved is greater than or equal to n square, right? So I can replace the denominator by n square. So here you have n square, and r to the n minus m. So r to the n minus m is, oh no, sorry, n square. Then sum 1 over r to the n minus m times this quantity, m plus r1 max A plus max B times max modulus of Cm. Okay. So I mean, I just want to write it in a way, yeah, maybe, because again, this is too strong. I mean, we don't need such a strong condition. So I will write it in a way which is, so let me take one n inside, okay? This one n, I keep one n inside. And this whole thing, it's sufficient to just say that this whole thing is less than some number, which I will call kappa, okay? Some number k. Okay, so the idea is the following. So you see that, I mean, so if you open this up, there's a m over n times max A, okay, plus some r1 over n, max A, plus max B over n, right? Okay, well, n is certainly greater than or equal to 1, right? So I can already say that this is less than or equal to, I mean, I can just replace this n by 1, correct? Because we are looking at upper bound. So I can as well just write it as max B. You see, this is very, I mean, not at all strict. You know, it's because we don't need it. I mean, okay. Then here again, I can forget about this n. So here you get R1 max A. And here, you see m over n, because the range of sum is m equal to 0 to n minus 1. This is always something which is less than 1, right? So I can again replace it by 1. Okay. So this is max A again. Okay. So the point of doing this was that to make something independent of, because I have to sum, you see. I want to make it independent of this m. I want to put some bound which is independent of m. Okay. I mean, the right hand side is much bigger than that, you see, because I have replaced this n by 1. I mean, suppose n is 1 million or something. Right? This is a, so it's a very, I mean, safe bound. Huh? But so this is going to be, okay, some finite number, right? After all, R1 is fixed, all this max A is fixed, max B is fixed. So this is going to be less than some number kappa, which I can always take this kappa to be greater than 1. Correct? I mean, suppose, for example, this was 0.1. Well, 0.1 is certainly less than 2. We are looking for an upper bound, right? So but the point is that all of this thing is less than some kappa, okay, where this kappa I can choose to be greater than 1. Okay. So at the end of the day, we find that all of this expression, I mean, then becomes the following. So this is less than or equal to kappa over n, where kappa is this bound for all that, okay, times sum 1 over r to the n minus m Cm, m equal to 0 to n minus 1. That is the kind of expression we have. Okay, so now we just start looking at this, just the first few terms, and you'll see a pattern. Is that clear? I mean, are the steps clear? And so just saying that this, I can always say that this is greater than or equal, this is less than or equal to some number kappa. Okay, the point to show that this is less than, to show that this is bounded. I mean, certainly these two terms are bounded. I mean, in fact, as you take n larger and larger, this just becomes 0, right? Because this is fixed. But this term, of course, if you take n large, m can also be large, because this is summation here, right, for the m. But nevertheless, whatever it is, this is some number which is less than or equal to less than 1, right? So upper bound is just some. Basically, for large n, upper bound is simply max A, because these things go to 0 for large n. But it's enough. I mean, it's all I'm to say that that is a bounded, and so therefore I can always say that this is less than some number kappa, which is greater than 1. So you find this relation. Okay, and now let us just look at the first few terms. Okay, and this I can erase now. So let's take C1. Therefore, is, let's see, less than or equal to. See, is there some number I'm missing here? No, kappa or n, correct. So Cn, you get here kappa less than equal to kappa times C1. So you see m is just 0, so it's just 1 over r C0. Right? Now let's look at C2. Now C2 has 2 terms. I mean, right hand side has 2 terms. Well, first of all, this k kappa over 2. Then you get here inside the sum. Well, m equal to 0 means 1 over n equal to 2. So C0 over r square, that's the one term, m equal to 0 term. And m equal to 1 term is C1 over r, right? But now use this fact that C1 is less than or equal to that. So you see, can I just do it in this line itself? Because otherwise, so just write so C1 is less than that. So therefore, I can write this as kappa over r C0, because again, I'm looking at upper bound. So now you see, so what you get here, C0 I can take out as a common factor. And then you get here kappa over 2, kappa over r square, kappa times, sorry, kappa plus 1 over 2 r square. Correct? I mean, this 1 over r, this makes a 1 over r square. So, okay. Now, I mean, so this, let's see, again, since I have chosen kappa greater than 1, see, this guy is less than or equal to 2 kappa square, right? Because this is kappa square plus kappa. But kappa is less than, is greater than 1. So kappa square is less than kappa. So I can replace the second term by kappa square. So, and this 2 cancels. So the upshot is that this is less than or equal to kappa square over r square C0. Okay? And you keep going. So now let's see, so how will be the structure? Let's see. I will go one more step and then you see the pattern. Now look at the C3. So now I have kappa over 3. You see, this roll of 3 is, roll of this n is that. Because basically there are n terms here. And that n cancels that n. Okay? That's the idea here. So here there was a factor of 2, but there were 2 terms, right? Each of them I can, here it is, there's a kappa. Here there is no kappa, but this is going to be, of course, less than if I replace by kappa. So just replace everything by the highest power of kappa, and then they all add up. And that number of n will cancel that. That's why it's happening. We'll just see one more term and then we'll. So this becomes first m equal to 0. So 1 over r cube C0 plus the second one is, 1 over r square C1 plus 1 over r C2, right? Now use the fact for the C1, which is this. So this becomes, again, replace this by C0, and this is kappa or r, so makes it r cube. Here is C2. C2 is kappa square. So there's a kappa square, r square times r is r cube again, and this is replaced by C0. And now C0 over r cube I can take out, and this you get 1 plus kappa square as a coefficient, once you take out C0 over r cube. But this is less than 3 kappa square, right? And 3 cancels, so you get kappa square times kappa cube. So this is always the case. You see, this is less than kappa cube over r cube C0, right? So in general, you can, this way you see that Cn is going to be less than kappa to the n or r to the n C0, right? So this is geometric series now, you see. I mean, you plug that back in the original expression. Let's see. So now I can erase all this because that's basically we have this bound. And this is a very, very safe bound. I mean, we have been very liberal in the bounds. Actually, you could have made it much more stricter, but we don't need to. So now go look back at the expression u1, which was z minus z0 to the power of r1 times cn z minus z0 to the n. So modulus of u1 is less than or equal to modulus of z minus z0 to the r1. And then, sum over n equal to 0 to infinity, modulus of cn, which is, we are saying is less than kappa to the n over r to the n. And then here is z minus z0 to the n. C0, times C0 is a common factor. Yeah. But you see, this series is just geometric series. And the radius of convergence clearly is r over kappa, right? I mean, so this must be less than 1. That's what we're saying. So this radius of convergence z minus z0 is less than r over kappa. It's convergent, and is uniformly convergent in that region. Okay, so that proves the. Okay, so okay, this was fine. I mean, I mean, more or less, I think even without this proof, you would have believed that this is convergent. But anyway, just to give a proof. Now, I think more interesting thing is the second solution, and I mean, interesting, more subtle things are there. So let me discuss the solution for the U2 solution, where the leading behavior is R2. Let's discuss that. But if are there any questions in this estimates? If not, I'll proceed to the next solution. I mean, the U2 solution, and then maybe work out a few examples of different possibilities. No. So as I said, if difference between R2 and R1 is not an integer, you can just plug that in. The same, you can play the same. I mean, you can determine Cn because the coefficient of Cn is never 0, even for the second solution, and so therefore you can write down the series for that. So the interesting case is when the difference is an integer. In that case, we will use the what do you call this Wronskian approach. So let's. I mean, this was from the very beginning of this chapter, so I will try to. Yeah. So U2. So let's consider the case where R1 minus R2 is some integer n. Okay, this capital N is an integer and is greater than or equal to 0 for because we have already said the real part of R1 is greater than or equal to real part of R2. So with that convention, this is always non-negative integer. So now if I try to, I mean, so let's try to use that. What is it called? The method of variation of constant, something like that it was called, right? It was the very beginning. Variation of parameters, yeah. Where was which page? It was. Correct. Here it is. 2. Yeah, U2 is, so the equation, so the method of variation of constants. So the idea here was just to write U2 as U1 times something, times some function h, and then just plug that back in the original differential equation. And use the fact that U1 already solves the equation, then what you find is that, so I mean the equation must be 2 U over dz2 plus P du by dz plus Q, that's Q times U, that's equal to 0. When you plug that in here, there will be I mean, the term where h, there is no derivative of h. I mean, these derivatives can hit here or there, right? So concentrate on the terms where there is no derivative on h, right? That means all the derivatives acting on u1. But then h comes out as a common factor, and you just get the same equation, I mean, same term, but just u replaced by u1. But by assumption, u1 satisfies the equation, so that term is 0. So the upshot is that when you plug that in here, there is no term which does not involve a derivative of h. So every term must have some derivative on h. So it can be only of the form dh by dz times something, or d2h by dz2. That means it's a first order differential equation for dh by dz, and this is the main idea. So first you solve for dh by dz, and then you integrate that again, you get h. At the end of the day, what we found that the solution was h was given by, so if I think h is given by, so in fact I can write down u2. So u2 divided by u1, which is h, u2 divided by u1 is h. This is some constant times u1 times integral 1 over u1 square e to the power of minus integral of p. Okay, you can choose some point to the point z. So this is at z, and here I choose again some point z naught to. So this is at z prime, dz prime, z prime. Okay, and this is pz double prime, dz double prime. Right. This was the solution. So it's the two integrals have to be done. The first you solve for dh by dz, because that's the first order differential equation for dh by dz. So dh by dz is basically given by such integrals, and then you plug that in back and integrate once again. That's why there are two integrals. Okay. So let's see how we can, in our case now. This was just quite some time back we did. I hope you remember this. What is this? Yeah. So in fact, let me just go one step back. Actually, instead of doing this, let me just derive it. Let me just start from beginning. This is the final expression we already obtained, but let's just plug that in. Let's plug this here. So you get from here, let's just do this. So you get here, as I said, d2 u1 by dz2 h plus 2 du1 by dz dh by dz. I mean, you see, this 2 factor of 2 is coming because two derivatives I can distribute in two different ways, right? That's why this is a combinatoric factor too. And then there is a u1 times d2 h by dz2. All that's coming from here, okay? Plus p times this, which is du1 over dz h plus p times u1 times dh by dz. And then finally q u1 h. That's equal to 0, right? That's the equation. But now if you concentrate on this part, this term, and this term, and this term, that vanishes because h is a common factor, and the rest of it is just a differential equation for the u1, and u1 is a solution. So this goes out. And then we are left with this solution for the, so equation is d2 h by dz2 times u1 plus there are two terms here, so 2 du1 by dz plus p u1, this whole thing times dh by dz, that's equal to 0. So I can divide this by u1. Okay. So now we have just a differential equation for dh by dz. So let's just do step by step. Let's see, what do we get? So h, so I can divide by dh by dz, right? So then this is just simply d by dz of log dh by dz. So, so what we are saying is that log of dh by dz plus this gives you 2 log u1, and then I have this integral of p plus p integral of p. Right? I mean, this symbol just means it's an indefinite integral. I mean, this is indefinite integral equal to 0. So therefore, that's a plus a constant. This up to a constant. So therefore, dh by dz is some constant divided by u1 square. You see, I take this. This is equal to 0. Take it on the other side, and then take the exponential of everything. Right? So you get here 2 dh by dz is, because it's on the minus side, you get 1 over u1 square when you take the exponential of this, and then times the e to the power of minus. That is the expression we had before. P. Okay. So, so let's see. Now remember what was P. P was A0 over Z minus Z0 plus A1 plus A2 Z minus Z0, etc. Right? The series. So when I integrate the P, what is that? This gives you A0 log Z minus Z0. Then from here is just okay. A1 times Z minus Z0. I can write it like that. And then you get here plus 1/2 A2 Z minus Z0 square, etc. Right? So it will be. Okay, so let's plug everything. And you see that you get here some constant. Now, u1 square itself starts with Z minus Z0 to the power of 2r1. U1 started with Z minus Z0 to the r1, so square 2r1. And then I have a series. Or maybe I shouldn't use this C. I mean, not to, okay. Cn Z minus Z0 to the n whole square, right? I mean, this is sum, sorry, there is a sum here. Sum n equal to 0 to infinity square, this square. And here what we find, this e to the power of minus this whole thing, right? So this gives you already, since this e to the power of minus of that gives you Z minus Z0 to the power of minus A0, and then the exponential of this whole thing. So times e to the power of minus A1 Z minus Z0 and so on, right? And these are, I mean, dot dot dot, because there's no singularity here. These are all just powers in positive powers in Z minus Z0. So we can rewrite this whole thing. I mean, so let's look at the leading behavior. There is a 1 over, if you put that together, it becomes 2r1 plus A0. Okay. But remember, we had this, what was R1 plus R2? R1 plus R2 was 1 minus A0, right? So if I plug this in here, so I mean R2 therefore is R1 minus n, right? R2 is equal to R1 minus capital N. Plug that in here. So this equation is simply 2R1 minus n equal to 1 minus A0, right? You just combine this, substitute R2. R2 equal to R1 minus n here. So you get here 2R1 minus n equal to 1 minus A0. So 2R1 plus A0, which is what you will get here when you bring this down here. So 2R1 plus A0 is 1 plus capital N. Okay. So this entire expression looks like this. So this is some constant divided by Z minus Z0 to the power of n plus 1. Okay. And then there is an expansion here. So I mean, I can make it, this rest of the part is analytic, near Z equal to Z0. I mean, this exponential of this are positive powers. Here also positive powers, right? So I can make, I mean, this starts from C0 square, which is non-zero, right? Plus order Z minus Z, plus expansion in Z minus Z0, right? So I can do the binomial expansion, I mean, geometric series expansion. So it will be all, I can write it in terms of Taylor series. So it will look like this. It will be some constants, I don't know, what shall I call, B, not B, C, D, D, Dn, Z minus Z0 to the n, okay? N equal to 0 to infinity. So this is just a Taylor series of all of this remaining part, all of this part here, because that's analytic, that part. So it will be, these dn's will be complicated combinations of these ans and cn's, no? Be very complicated combinations, but nevertheless, whatever it is, it will be some expansion like this. Okay. And you have that. Now let's, you have to integrate one more to compute h, right? So what will that be? So I integrate that. So h therefore will have the leading term will be again some constant, let's call it f0, which will be a combination of all of this. I mean, f0 divided by z minus z0 to the n. That's the leading term, right? I mean, that's the leading term there, right? And then there will be lower powers, say f1 z minus z0 to the n minus 1, right? I mean, that comes, first term comes from the taking n, little n equal to 0 here. So that will be some constant divided by z minus z0 to the n plus 1. Integral of that will be some constant divided by z minus z0 to the n, right? When you take little n equal to 1, one of the power cancels, integral of that will give you power n minus 1 down, right? And so on. So this keeps going, f2 z minus z0 to the n minus 2, etc. But what happens to the term when small n equal to capital N? You see, look at the particular term, small n equal to capital N, this capital N. In that case, z minus z0 to the capital N cancels with this n powers, and you're left with 1 over z minus z0. Integral of that will give you log. So you see, there is a term that will be, which actually I can write on explicitly. That term is the term which is coming with a d capital N. So c times d capital N log z minus z0. That is see, that's a new term. And then, okay, for small n bigger than capital N, you will just get positive powers. So the rest of the powers are all some powers. Rest of the terms are all powers of z minus z0, right? With the worst negative power being capital N, and then everything else less negative or positive. But if this coefficient d capital N is not 0 in that expansion, right, then you also have a logarithmic term. So that's a new term. So that was h, and so therefore what is u2? u2 is simply h times u1, right? So for example, these terms are of the form, I mean, look at the leading term. So that means z minus z0. Well, u1 itself is z minus z0 to the r1. But combining this, you get a minus n, right? I mean, after all the rest of the terms, I can take out this 1 over z minus z0 to the capital N, and then write everything else as some analytic Taylor series. So it will be, I just take the leading term, and then some expansion, I don't know, f, let's call it g n z minus z0 to the n, right? That is except the log. I mean, I'm taking everything else, right? Everything else can be written in this form, okay? u1 is z minus z0 to the r1 times that all the cn's at the Taylor series. All of these remaining parts, I can write it as 1 over z minus z0 to the capital N times something again, some series, analytic series. Take that product of the two analytic series, I can rearrange the terms again like this. So this is the form. And then there is also this additional piece, again with some constant times u1 z times log z minus z0. You see. Now, if you look at this r1 minus n, I mean, I just erase this equation, r1 minus r2 equal to n, right? So r1 minus n is in fact equal to r2, right? So this would be r2. So you see, if I had not put this term, I would have just, that was our original answers for the u, right? I would have tried that, and I would have found an inconsistency, right? Because at some point I cannot compute the C capital N, right? Because the coefficient vanishes. And the problem is that I was ignoring this term. My ansatz was not good enough. I had not included this logarithmic branch cut. I had only allowed kind of power law branch cut, somewhere R2 is not an integer or something, but not a logarithmic branch cut. I had not allowed. So my original answers was not complete, right? That's why, so we need to add that. Of course, not always this term may be present. I mean, that depends on whether dn is 0 or not. D capital N is 0 or not. It can happen in some particular types of differential equations. Okay, that depends on the choice of the P and Q. For some specific choices, it may happen that this coefficient is 0. Okay, in which case this term doesn't appear. Okay, but generically you'll have logarithmic term. I mean, those will happen in very, very special cases where the D capital N vanishes. Now maybe I'll just consider some examples, different types of examples. Examples where D capital N vanishes, and another example where D capital N does not vanish. Just to get some feeling for it. Well, I mean, yeah, okay. So let's see. If there's no question, I can just go on to the example. Yeah.
How can we interpret this result? Well, we have some power of minus 10, and
that's so
before
difficult.
getting on power plus n, we have
Sure.
the logarithm.
Yeah. It's, I mean, if capital N is large, it's, I mean, to do analytically this calculation will take you a long time. Yeah, surely. Because as you say, you have to go up to power 10. No? And that too is not some simple thing because you have to multiply this. There are two different series here. You have to multiply them. I mean, exponential of one series and this another series square. So, you know, to go up to order 10 will be horrendous. I mean, you know, but you can put it in the computer if you know these coefficients and compute it. But I mean, this is not so much. This is mainly to prove this statement that generic solutions are not. I mean, the fundamental set of solutions are of this type. So you remember U1 is z minus z0 to the power of R1 times some power series. I mean, times some integer power expansion, n equal to 0 to infinity Cn z minus z0 to the n. And U2, but so one of them you can always find like this, one solution, where this satisfies the indicial equation with the real part of the greater one, whose real part is greater one. U2, on the other hand, generically is not of this form, right? I mean, it's of this form if the difference is not an integer. If the difference is an integer, in general, you need to introduce also this extra piece, the logarithmic piece. That's what basically, this is just proving that statement. Of course, as you say, if in practice, if you have to really solve an equation for some given, you know, capital N, it will be a mess. I mean, you know, unless this capital N is small, you know, like 1 or 2 or something, maybe you can still do it. But, you know, for large values, it's very difficult. But in principle, doable. You see, it may take you 2 or 3 days of, you know, algebra, but in principle, it's doable. No? Yes. Yes.
And if the electron change the states, can we apply this?
No, I don't see how you can. I mean, no, it's. And it
physics sense of this form.
I don't know where it appears. I mean, you know, it appears in many places, but I probably not. How to say? I mean, I don't know if I say it will be just words, because okay, there is I know personally some particular examples where this appears, physics example, and that appears in two-dimensional conformal field theories. Okay, in conformal field theory, basically scale invariant theories. You know, there are certain quantum field theories which are scale invariant. Normally, the theories are not scale invariant, right? Because scale is what? Some unit dimension, right? So, I mean, for example, if the theory has a mass, if some particle has a mass, that theory cannot be scale invariant, right? Because when you change the scale, you are scaling the mass, right? But the theory clearly depends on the mass, right? So, but there are some theories which are called conformal invariant theories. Those theories are the ones where if you change the length scale or the mass scale, the theory doesn't change. Okay, and they play a very important role in many phenomena, many critical phenomena. You know, near the phase transitions, basically the theory can be approximately described as a conformal field theory. Okay, so in the two-dimensional conformal field theories are, you may imagine that they are like theories which are good approximations to a phase transitions phenomenon in 2 dimensions, right? So 2 dimensions, why 2 dimensions? Because many of the condensed matter problems have they make one direction symmetric. You know? I mean, so the system does not depend on one direction. System depends only on 2 directions, and then that will be, you know, example. Then 2-dimensional conformal field theory also appears in string theory. I mean, it's completely, string theory is based on 2-dimensional conformal field theories, right? And in those cases, generally when you look at some operators, there is the notion of correlation functions of the operators. So the correlation functions of the operators are typically given by solutions of the differential equation. Meaning, what you can do is that you write down the correlation function. Because of the scale invariance, these correlation functions are highly restricted because scale invariance is not a, I mean, it's a very unusual thing, right? So obviously, it's going to impose some restrictions on the correlation function, okay? And you can prove that those restrictions amount to certain differential equations on the correlation functions, okay? So for example, if you look at the 4-point function, 4 operators, you insert 4 operators and you look at the correlation function, how they are correlated. I mean, you know, that's what it means, correlation function. And you can show that that correlation function obeys a second order differential equation. Okay, not sometimes even higher order differential equations. But the simplest case is when it obeys a second order differential equation. And those are the, there you see all this, you know, singularity structures. You know, sometimes it could be log, sometimes it could be just power laws and so on. No? And those singularity structures have got to the meaning of, I mean, so you're looking at the 4-point function here. So it could, so this, I mean, this, by studying these different singularity structures, what you're identifying is diagrams like this. I mean, so 2 operators merge together to give you an intermediate operator, intermediate state. And the singularities associated with these channels are are given by these numbers. Okay. So they have, but I'm sure it has probably other applications also. But these 2 applications I know. I mean, probably they also appear in other cases. So let me just take some examples and yeah. So first. So consider an equation which is of this type. U du by dz, d2u by dz2 plus, okay, there's no reason for this, but I mean 3z minus 1 over z times z minus 1. Okay, this is my p. This is p times du by dz plus q, which is simply 1 over z minus 1 u equal to 0. So you're looking at this equation. So let's see what are the inducible equation near z equal to 0. So I expand around z equal to 0. At z equal to 0, there is a pole, first order pole here. And here there's again only first order pole. Yeah, it's only first order pole here again, right? So A0, you can see is simply, I mean, if I write it near z equal to 0, this will have expansion. Well, I can write this as, so this term is 3 divided by 1 minus z, so minus 1 minus z, and minus so plus 1 over z times 1 minus z, right? That is this term. This z cancels with that z, so there is one term here. The pole is only appearing here at z equal to 0. That is regular, right? So you can expand this guy. This term is 1 over z, 1 plus z square, and so on and so forth, right? That term. So A0 is simply this term, 1. So what this tells me that A0 is 1. And B0, there is no second order pole. B0 is the coefficient of second order pole in Q, right? So B0 is 0. So the initial equation was r square minus 1 minus a0 r plus b0, right? Plus b0 equal to 0, but b0 is 0 anyway. A0 is 1, so this also drops out, and the solution is r square equal to 0. I mean, there are two roots, both are identical, r equal to 0. Okay. So question is now, so of course I can choose r1 equal to 0, r2, I mean any one of them, r2 equal to 0, right? And we should be able to solve for r1, I mean the u1 solution. And then u2 we cannot determine by expanding because difference is an integer, 0 is an integer, right? So second solution we have to determine by the method of variation of parameters, constants. Okay. So let's first determine u1. Well, and then we can try to see if it has a. So let's try to get the. Maybe I can just directly. So what is p? Let's write down p. So p, I can write it as this expression. So here you get. So there are two terms. So the 1 over z, that's the leading term. Then you get the constant term here is 1. Here it is minus 3. I don't know if that's the best way of doing it. Yeah, okay, let's see. Minus 3. Yeah, you also expand that. So this is minus 3 times 1 plus z squared, etc. Probably I think it's enough to just get the first few terms. So I'll just write down the first few terms. So you get here, from plus this, right? So first term is 1 over z. Second term is the constant, which is 1, but also there's a minus 3, so minus 2. Then you get, I'm sure there's a better way of doing it. Okay. Then you get next term, which is z. From here, again, minus 2z. So it seems that's all going to be minus 2 everything, right? I mean, this whole thing is minus 2z square. That's the point. I'm sure this we should have been able to get it in a much more simple way. Yeah, I think I could have, because after all, I wrote it in one way, 3z minus 1 divided by z times z minus 1, which I can write it as minus 3 plus 2, right? So this first term is 3 times z minus 1, so z minus 1 cancels. So you get here 3 over z. And the second one is minus 2 over z times 1 minus z, but 1 minus z expand. Okay. So that's why the first term is 3 over z minus 2 over z, 1 over z, and the remaining pieces are simply minus 2 times z plus z square plus etc. Yeah, that's p. And q again, I can write q is 1 over z times 1 over z minus 1. I can make a partial, I mean this fraction thing. I can write it as 1 over z plus maybe, let's see, 1 over z minus 1 over z minus 1, or maybe other way around. Yeah, minus that, right? Yeah, minus that and plus that. Correct? So that's. Okay, which is the same as minus 1 over z. So minus I can take out, and plus 1 plus z squared. So a very simple expansion actually for these functions.
1 plus z squared.
Sorry?
Minus 2 times 1 plus 8 plus.
One plus 8. 8.
No, 1 plus 8 plus, we have
Z. Yeah. We have written 1. Correct. Yeah, 1 plus z. Yeah, correct. Yeah, 1 plus z. Yeah, exactly. Yeah. Sorry, here, this one. Here. No, because this is z minus 1, right? So I write it as 1 minus z. Yeah. because then I can make an expansion geometric series. Okay, so then we plug this in here in the differential equation, and we can write down this recursion relation. And what was the recursion relation? It was this is a bit going to take some time, I think. Yeah, the recursion relation was this here. So you have, so we start with the z minus z0 to the power of r1, but r1 and r2 are 0, so that is 0 to the power of 0, and then z minus z0 to the power of n cn, n equal to 0 to infinity. So this is say u1. You plug that in here, and the equation we get is n times n minus 1, because r1 is 0. Otherwise, it will be n plus r times n plus r minus 0, 1, plus n a0. A0 is 1, so that's n, and b0 is 0. So this times cn, okay, plus some m plus r. Again, r is 0, so m a n minus m plus b n minus m. Cm, m equal to 0 to n minus 1. This is equal to 0 is our equation.
Before the sum.
It's a plus, right? I mean, I'm on the left hand side. If you put it on the right hand side, yeah, it will become minus. This is in 14.27. Yeah, if you move it on the other side, it will become minus. Yeah. So this is very simple. It's just well, n cancels. We just get n square cn, and let's look at this combination: m plus an minus m, bn minus m, m equal to 0. So here we are saying, what is this? Tells me that a0 is 0, a0 is 1, and all the higher terms, a1 equal to a2 equal to a3, etc. This is all equal to minus 2, right? From this, and from here we see that in fact all, b0 is 0, and all of the other ones, b1 equal to b2 equal to b3, etc. equal to minus 1, right? So the only exceptional case is the 0 one. I mean a0 and b0. Everything else has the same value. These are all minus 2 and these are all minus 1. Now, in this sum, this will never be 0, because m goes from 0 to n minus 1. So n minus m will never be 0, right? So this can only be of this type or this type, right? So this will always be minus 2. So this is always going to be minus 2m plus b0, which is minus 1. Okay, that's the expression. So n square cn. So I can take minus outside, so plus, minus 2m plus 1, minus 2m plus 1 cm, sum m equal to 0 to n minus 1. That's equal to 0, you're saying? Is it, yeah. In fact, this is, yeah, it looks pretty, it's very, I mean, these coefficients are, this is very simple, right? I mean, general functions, these coefficients will be horrible, right? But here, just because it was so simple that we were able to write something like this. Yeah. So I don't know, we have to probably see some first few terms. So let's say, so C1 is equal to, so we have just C0, right? Because for n equal to 1, this is just m equal to 0. There's only one term. There is a square.
The sum is m squared. The sum to m plus 1.
No, but this depends on m. So you cannot sum. Cm, yeah. So C1 is C0. Now let's look at the n equal to 2. So this is n equal to 1, n equal to 2. So C2, 4C2 is equal to n square, 4C2. There are two terms here. M equal to 0 is just simply C0, and m equal to 2 is m equal to 1 is 3 C1. So plus 3 C1. C1 is C0, so this is 4 C0, which means C2 is also C0. So you see, actually they're all independent of, right? I don't know, can we prove by induction? Yeah, I mean suppose, so this is true, right? C1 is C0, C2 is C0, okay? Now suppose that it is true that the first up to n minus 1, C0 equal to C1 equal to C2 all the way up to Cn minus 1, okay? Then I want to show that Cn also is equal to C0, right? Then we'll have proven completely. So if I, so let's see, so I want to look at this nth term, because this is true up to n minus 1. So we have n square Cn equal to, I take it on the other side, so you have 2m plus 1 Cm m equal to 0 to n minus 1. But we said that for all of these values, Cm is the same as C0, so I take it out, I can take this out, it's independent of m, and now you can do the sum, right? So this sum is what, equal to C0, is it really m square only? Okay. I mean, let's say the first term gives me 2 times n minus 1 times n over 2, right? The first term, and the second term simply gives me n. So, yeah, indeed, this cancels with that, you just get n square. N square cancels, and so therefore Cn is also equal to C0. So by induction, so it's an amazingly simple solution, right? So we are finding that this entire thing is just a geometric series. So this is simply C0 times Z0 is 0 for us, and we are expanding around 0. Simply 1 over 1 minus Z. That's it, U1. Actually, you should be able to see directly, I mean, without any series solution. It's so simple, if you try to plug that in here, I think you should be able to check directly, right? That's, I mean, it has to be. Unless we have made some mistake, this should satisfy, right? But, okay, so this is amazingly simple, really, yeah. So now let's go to the second solution. So for the second solution, we had, first of all, dh by dz was, I mean, the equation was d by dz of dh by dz. This is the method of variation. We write u2 is equal to u1 times h, right? And then get that was equal to minus 2 over u1 okay, minus 2 over u1 minus p, right? Now 2 over u1 du1 by dz, yeah, minus p, correct? That was I mean, we some time back, we just, I mean, a few minutes ago we wrote that, times dh by dz. Okay, so we find that log of dh by dz. So what is this? Let's actually, since we know u1 is so simple, we can explicitly work it out. No, or not. Just okay, we can maybe just leave it as it is for, or we can simplify it. So du1 by dz is 1 over 1 minus z squared, right? And then u1 is 1 over 1 minus z, so this whole thing is C0 cancels, so you get here minus 2 over 1 minus z. I know d by dz of this is plus 1 over 1 minus z squared, because there is a minus here, you see. Yeah. I mean, if you are written as z minus 1. Yeah. And p is that which we already said is actually, yeah, in fact, p is that which we already wrote like this. This is minus 1 over z plus 2 times this whole thing, but that's again 2 over 1 minus z. So this combination is simply 1 over minus 1 over z, right? It's quite simple. So this cancels, and you get d by dz of log dh by dz is equal to minus 1 over z. So it's 1 over minus log z. Now I'm sorry, d by dz is minus log z. So dh by dz is simply 1 over z times some constant. And therefore, h is c log z. Right? Some constant times log z plus another constant. And therefore, the second solution, so u2, so u1 was very simple, what we said. U1 was simply 1 over 1 minus z, that was u1. And u2 is simply log z times u1, because h is the ratio of u2 over u1. So u2 is simply log z times u1. So there is a log z here. Actually, you can show that, you remember I mentioned that log z will not be there if that coefficient d capital N vanished. But for in this case, capital N is 0. You can show that d0 never vanishes. Right? So when the two roots are coincident, then log will always be there. Second solution will always have log. Okay. Okay. I don't know if I can I do also another example. Let's see. Okay, let's do. Let's see another example. Yeah, let's do another example. Maybe x square. Again, it will be simple types of objects. So that I mean, here the reason why this became so simple was these coefficients are very simple, right? There's a pattern, right? When you have a pattern, you might be able to solve. Otherwise, for generic things, it will be very difficult. So this is again a very simple equation. Actually, it's a kind of a Bessel equation, but we'll discuss that later. At the moment, just see what it is. It's so it's d2u divided by dz2 plus 1 over z du by dz plus 1 minus 1/4 z square u equal to 0. Okay, we consider this equation. So here now, I mean, so p is simply 1 over z. So that's it. I mean, so and we want to expand around z equal to 0. If z equal to 0, there is a regular singular point. First order pole here and second order pole there. Okay, and q is 1 minus 1 over 4 z square. So in this expansion, there is only, I mean, p has only one term and q has only two terms. So a0 is 1. And b0 is minus 1/4, and that's it. And b1 is 0, and b2 is 1. That's it. Everything else 0, right? So it's very simple. So we plug that. So look at the indicial equation. So indicial equation is r square minus 1 minus a0 r. So 1 minus a0 times r. That cancels, and what is left over is b0. So minus 1/4. Equal to 0, right? So the two solutions are r equal to plus or minus half. And now you see that difference is an integer, but not difference is 1, right? So r1, I call r1 as plus 1, plus half, and r2 is minus half. Because real part of r1 is greater than or equal to real part of r2. Okay, so now let's see what is the recursion relation again. Okay. So recursion relation is C. Yeah, Cn. I mean, so n plus r1. So that is n plus half, n plus half times n plus r1 minus 1, which is n minus half, okay, plus n plus half, for this is for r1, r equal to r1, n plus half times a0 is 1, and then plus b0 is minus 1/4. That times Cn plus sum m equal to 0 to n minus 1, and you have a n minus m. So okay, sorry, m plus r, m plus half, a n minus m plus b n minus m, c n equal to 0. So can we simplify this? So you get here n square minus 1/4. So minus 1/4 minus 1/4 is minus half, which cancels this plus half. So there's no constant term, I mean an independent term, and the n dependent term is simply n square plus n. So this whole thing is simply n times n plus 1 times Cn. And here in this sum actually most of the terms are 0 because you see only a few terms are non-zero, right? In fact, you can see that this can never be 0 in this range. I mean this is never 0, it's not ever a0 or b0. So the only other term which is non-zero is b2. That's the only term, right? So in this whole thing, the only term which will appear is when this is equal to 2, right? Which means m is equal to n minus 2. That's the only term which survives. Okay, and in that case, b2 is simply 1. So this whole thing simply is c n minus 2 times 1. That's what it is. Yeah. So the equation becomes so cn equal to minus 1 over n plus 1 cn minus 2. That's sorry. M equal to n minus 2. Yeah. Because we said, I mean, because this must be equal to 2. N minus m should be equal to 2, right? But that means m is equal to n minus 2. Right? Because that's the only term which is non-zero. Everything else is 0. So b3, b4, everything is 0. And similarly here, a1, a2, everything is 0. Well, m equal to 0, m goes all the way from 0 up to n minus 1, right? Yeah, but it can, there's no other value, you see. This can never be 0.
Yes, for 2b, 4 equals 0.
Let's see, I mean, so when can this be non-zero? This has to be, this argument, this index, n minus m, has to be either 0 or 2, right? That's the only possibility, right? But this cannot be 0 because the range of sum is from m equal to 0 up to n minus 1, right? So the only possibility is this can be 2, right? And similarly here, I mean here, in fact, this n minus m can never be equal to 0, so it can never be a 0, so everything else is 0. So that's the only possibility here. And this you can immediately write down what it is. So I mean, actually this gives you relation, a two-step relation, right? N to n minus 2. Now, if I write something like our solution u1 is z minus z0 is 0 to the z to the power of 1/2 times c0. C0, remember, is not 0, right? Then what this relation is telling me is the relation between all the E1 terms. So C2 will be related to C0, then C4 will be related to C2, and so on, right? So it gives you the E1 series. So C2n, I can say take n equal to 2n, then that gives me is equal to minus 1 over 2n, just replace n by 2n. So 2n plus 1 times C 2 times n, 2 n minus 1. So immediately you can see the relation. So C2n is simply, what is it, factorial, right? So factorial 2n plus 1. 2n plus 1 factorial, and there is an alternate minus sign, so it's minus 1 to the n C0. Okay. So this expression is up to some C0 constant is simply minus 1 to the n over z, z times z to the power of 2n and factorial 2n plus 1 sum. right? Some n equal to 0 to infinity. That's what we are finding. Because remember, so what are the thing? Maybe I moved through a couple of steps. So this is giving me the relation between only E1 indices, right? Because I started with a C0. This tells me what is C2, then C4, and so on and so forth. So therefore, then so it's a relation between all even ones, even guys. So I might as well replace n by an even number. Think of n as an even number. So it will be some 2 times some integer, right? Just replace wherever you see n by 2n, you get that. And then I just substitute. So and then solution of this is this recursion relation is that you can explicitly see. That's no. I mean, just plug that in here. C2n and C2n minus 1 will be the same expression. Just replace n by n minus 1, right? And take the ratio of the two. You'll find this. You'll see that this satisfies. Just check that. Check that this solution, this ansatz satisfies this recursion relation. But this one, you know what it is. This is simply the expression of this sum of this series of sine function, trigonometric function sine. Except that if this had to be power 2n plus 1, right? So actually, what this is sine z divided by z, because I've taken out one z. So this expression is simply some C0 z to the half, which is outside, and this is sine z divided by z. Which you can write it as, this is the same as C0 over root z times sine z. That's the first solution, U1. And now we need to look at the second solution. Again, because the difference is integer, we need to use the method of variation of constants. So again, let's we write. Actually, what was the equation? dh, yeah. So d by d. So write u2 is u1 times h, and d by dz of dh by dz equal to minus 2 du1 by dz over u1 plus p, and then times dh by dz. Right? This was the equation. So p for us is 1 over z. Substitute that, and okay, and then we just integrate. So log of dh by dz is equal to minus 2 log u1 from there, but then there is, I find a log z minus log z, correct? Is that correct? Yeah. So dh by dz is equal to 1 over u1 square, and this is times z. So z, u1 square times z. So now you have to integrate that. So what is this object? This is, let's substitute that. So up to some, there's some constant here anyway. So that C0 I can absorb inside this constant. So u1 square is 1 over root z square, so z cancels. And then you get 1 over sine square z. Do you know what is the integral of this? This is cosec square, so it's integral is cotangent z, right? So h is basically cotangent z. Again, up to some constant. So then second solution u2 is simply u1 times h. So cotangent z, so sine z cancels, and we just get cosine z over root z, some other constant c0, let's say. So these are the two solutions. But you see now there's no log here. There's no log here. So that coefficient must be vanishing for this. Although we didn't expand here. I mean, we just this function is so simple that we could just directly integrate it. But if it was not so simple, we would expand it, right? We would expand in the series. And in that case, it should happen that there is no, that coefficient which controls the log should not be there. So this is so there are these two examples where in one case the log appeared, in the other case log did not appear.
But still there is the behavior of log.
Sorry?
But still there is the behavior of log inside the U2. I mean the branch can.
Yeah, but not a log. I mean, you see, this is exactly the behavior. So if you look at small z here, small z, sin z goes like z. So this power, the leading power is square root of z, and then you have expansion, 1 plus integer powers of z. Here, cosine z near z equal to 0 goes like 1, right? So this will be 1 over root z, n times 1 plus integer expansion. Integer power expansion. But that's what you expected because R1 is plus half and R2 is minus half. So this is z to the R1, z to the R2. Right? But the point is that the second solution in general was not just that. It was this type which had a leading term R2 controlled by power R2 plus the logarithmic term which was a different term. So in this case the logarithmic term is not there.